materials is the energy conversion technology can transport heat into electricity and vice versa. And by applying electric bias, hole and electron can transport entropy. Therefore, in cold side, heat absorbed side can be applied as a solid state cooling technology. And also, when we apply the temperature gradient, for example, the thermoelectric module can attach to the hot side, then the thermal gradient can induce the hole and electron. Therefore, it can generate a power generation. It can be applied to the waste heat recovery. Many thermoelectric scientists say that the GT value is defined by this relation, as means that Seebeck coefficient, that is the voltage difference by applying a temperature gradient, and the electrical conductivity, sigma, and the thermal conductivity. In order to have the high GT value, the S squared sigma means that power factor should be maximized while preserving the low thermal conductivity. This is a thermoelectric module structure. It's very simple. And there are two strategies of thermoelectric materials development. For example, nanomaterials. One is the nanomaterials, and the other one is the new materials design. For example, in the case of nanomaterials, artificial superlattice or the nanowire coherent structure nanoparticle synthesis and bulk nanocomposite and natural phase separation such as spinel decomposition are effective way to reduce lattice thermal conductivity. In the case of new materials, for example, rattling and the interface are a good strategy to reduce lattice thermal conductivity while preserving the electrical high transport. And resonance balance band and band structure engineering, these methods are very effective to increase the power factor. Here I propose another new strategy, and it is a very fundamental approach. Basically, Anderson localization is a quantum mechanical phenomena that was proposed by Professor Anderson. And in classical point of view, when we consider for random potential like impurities or imperfections, electrons can scatter between the impurities or imperfections like this. But in quantum mechanics, electron is not a particle but a wave like this. Therefore, the quantum interference of scattering waves can make Anderson localization, charge localizations like this. This strong charge localization by random potential, we call this is Anderson localization. There are several examples for Anderson localization in bulk materials. For example, titanium oxide interface, anatase and rutile interface can make oxygen vacancy. And oxygen vacancy can have charge trap, and the charge trap is kind of Anderson localization. And also, this iron selenide is a crystal structure of iron selenide is this tetragonal structure. But when we think about the lithium doping, and lithium doping is basically it is electron doping, but it generates that strong charge localization with huge electrical resistivity increase. Then it is due to the charge localization by the lithium ion. In solid state textbook, and the electrical current and heat current can be related with Ansgar relation by applying the electric voltage or a temperature gradient, and the electrical conductivity and Seebeck coefficient, thermal conductivity and GT value. Those kind of thermoelectric parameters can be expressed like in terms of Ansgar relation like this. This Ansgar relation, Ansgar coefficient can be calculated from the electronic response coefficient can be calculated like the Chester-Thurlow-Kruber-Greenell formula from this relation. Therefore, when we think about the Anderson localization, the thermoelectric properties can be calculated like this formula. Therefore, this conventional density state becomes the scale root energy behavior like this. And when you consider the Anderson localization, the extended state becomes a sharp localization, and we can see that the band edges and the strong band edges becomes the sharp density state, and the sharp density state means that the high ZV coefficient can be possible in these materials, and therefore we can calculate the thermoelectric properties like ZV coefficient and GT value in terms of reduced temperature. Therefore, when you think about the Anderson localization, the electrical conductivity versus temperature and the ZV coefficient versus temperature can be shown like this. At low temperature, because of the strong localization, the electrical conductivity becomes very low and the ZV coefficient becomes very low also, and at high temperature, it becomes ZV coefficient becomes saturating and non-linear behavior by expressing this formula. Here, I propose that another new concept. It is selective charge Anderson localization. It is not a perfect localization. The concept is that it is not clear. When you see at this picture, and this is a Fermi level in many thermoelectric materials has a narrow bandgap semiconductor, and because intrinsic excitation of a hole or the electron whole electron is essential. Therefore, bipolar transport is very inevitable phenomena. Therefore, bipolar transport is not good for thermoelectrics because the positive ZV coefficient by hole and the negative ZV coefficient by electron can cancel with each other, decreases the ZV coefficient, and as well as the bipolar transport of carrier increases thermal conductivity. Therefore, my motivation is that we should induce that selective charge blocking and in terms of Anderson localization. In the case of Fermi level resides in the bottom of the conduction band, it is anti-materials, but because it is a narrow gap semiconductor, basically whole excitation can generate and also decreases negative ZV coefficient. But when you think about that, the hole can be blocked by the strong localization of the hole, then the energy band gap also, effective energy band gap increases. For example, effective energy band gap is that energy intrinsic band gap plus cutoff energy. This is a large energy band gap can increase the ZV coefficient, and also bipolar transport of carrier can block by this strong charge, selective charge localization. The concept is this is an illustration in quantum mechanical point of view. Then electron, this is a matrix potential. This is a positive potential. This is negative potential. This side is the electron side. This side is a hole side. And the electron, when you think about the strong random positive potential, then electron is the electronic wave function becomes extended state, and we just assume that hole becomes a strong localization by the random potential, and therefore in this case the strong positive random potential can make electron can be tunnel with each other, and in hole side this random potential can be considered as a random quantum well. Therefore the strong interaction between the impurity or the imperfections and the hole can make a localized like this. In the p-type material case, p-type material is the majority carrier is a hole, therefore Fermi level resides the top of the valence band. And in this case, when we consider strong localization of electron, and like this, in here, the random potential becomes the strong negative potential comparing with the matrix material, and therefore then the electron localized like this. Therefore, the conduction band becomes cutoff energy and becomes localized, and cutoff energy plus energy band gap, the increase of effective energy band gap, and the strong difference between the electron and hole band. We theoretically calculated in terms of Anderson localization formula by using this formula. And here, this is an illustrative, this is cutoff thermoelectric parameters with respect to cutoff energy. Increasing cutoff energy means that increasing the charge localization, selective charge localization strength. Therefore, in the case of electrical conductivity, by increasing the selective charge localization and electrical conductivity decreases, and electronic thermal conductivity also decrease. But in the case of Seebeck coefficient increase because of the strong charge localization and the charge imbalance, and therefore the power factor also strong increase. Therefore, the GT value can also increases as much as 10 times comparing with the pristine compound. Therefore, how to realize this concept? One example is that the anti-lead telluride, because in the case of bismuth-doped anti-lead telluride case, it is the anti-Seebeck coefficient material, and also it can be tuned by the energy. It is very effective to the anti-materials. And here we choose that bismuth-doped lead telluride. It is stable anti-materials, and also as a random potential dispersion, we choose the silver telluride, and the because it shows that the structural phase transition near the 420 Kelvin, and below this temperature, the structure is a beta phase, and in the above this temperature, it is alpha phase. In the case of high temperature, the electrical resistivity is very high. It means that the energy increase the energy band gap. It is a semi-conducting state, and low temperature, the energy band gap becomes a metallic state. There is no energy band gap. Therefore, from the energy band gap structure calculation, in the alpha phase, there is energy band gap opening like this. It is a semiconductor state, and in the beta phase means that it is a metallic state. Therefore, metallic to semiconducting transition can be considered by structural phase transition. Therefore, we can compare with before and after this structural phase transition, because potential can be different in these two sides. We synthesize the silver telluride nanoparticle because random potential needs the nano size particle and the random distribution of particles. Therefore, we synthesize this kind of method. Therefore, we synthesize nanopowders from these roots. And therefore, we measure the TGD-TA measurements. It shows the very sharp peak near the structural phase transition, and it is very stable for repeating the heating for several cycles, and it is a stable silver telluride. Here this is lead telluride matrix. It's very clean matrix, and the bismuth-doped lead telluride becomes more. This is a strain field map of the lead telluride and bismuth-doped lead telluride, and strong strain field map in the bismuth-doped lead telluride means that the impurity or the imperfection is more efficient in the bismuth-doped lead telluride. And here we adopted the silver telluride composite distribution, and this is private is not an intrinsic case. It is extrinsic because when we make a FIB etching, and silver, silver is melted. And here, this white spot is a silver telluride nanoparticle, and the silver telluride nanoparticle can be identified by EDX measurement, and it is a silver particle. The size is about the 20 nanometer scale, therefore very small nanoparticle can be well dispersed in the matrix. And also when you consider for lattice parameter bismuth-doped lead telluride, the lattice parameter 6.5, and the beta phase and alpha phase lead silver telluride, the lattice parameter is similar to the bismuth-doped lead telluride. Therefore, the lattice mismatch is very small, and the coherent interface can be possible. This is thermoelectric properties. It is very interesting because in the parent bismuth-doped lead telluride and the silver telluride shows that the metallic behavior with temperature, but the small addition of silver telluride for just only 5% of the compound shows the insulating behavior. This kind of metallic to insulating behavior is consistent with the Anderson behavior, and it is an insulating phase. This is a conducting phase. In the case of Seebeck coefficient also, when we consider for the structure phase transition temperature, the Seebeck coefficient shows that the step-like behavior. This is beta phase and this is alpha phase. Therefore, the sharp transition can be considered in the beta phase and alpha phase. And also, the power factor shows that the high power factor at the high temperature range. Therefore, basically, the silver telluride composite is the random potential. Therefore, the lattice thermal conductivity decreases by adopting the silver telluride composite. This green one, and green one is that the bismuth stopped lead telluride, and the decrease of the silver telluride composite can decrease the lattice thermal conductivity. Therefore, the GT value shows that reaches about 2 in N-type materials. This is the exception of very high GT value in N-type thermoelectric materials, and it is kind of state-of-the-art value for N-type power generation system. Therefore, when we measure the low temperature thermoelectric properties, it is the metallic behavior becomes almost insulating behavior by adopting small silver telluride materials, and this behavior is similar to the Fowler's theory of Anderson localization behavior for this case. Therefore, it is very well described by the Anderson localization. And also, we examine these scanning tunneling microscopic images. It shows that this is a lead telluride material and the silver telluride matrix. And when we measure the scanning TEM microscopy, shows that the DIV map shows that the energy band gap is about 1.3 electron volt in lead telluride side, and the silver telluride shows that 1 electron volt. Therefore, when we illustrate the energy band diagram, this is at room temperature. The lead telluride has a large energy band gap, and a small energy band gap is anticipated in the silver telluride case. It means that it is a sharp step-like potential web. Therefore, because it is N-type materials, photon level resides in the conduction band minimum case, and but we should consider the structural phase transition. After the structural phase transition at high temperature, the energy band gap increases because it is semiconductor in alpha phase. Therefore, the increase of energy band gap means that interaction between the silver telluride and electron becomes very weak. Therefore, in this case, before silver telluride phase separation, in the hole and electron are both charge carriers are localized strongly by the silver telluride localization. But when we think about that, the silver telluride at high temperature, and the silver telluride undergoes the semiconducting transition and becomes a weakening of the interface charge and charge in the silver telluride interaction, and by weakening of the localization, electron becomes itinerant state, while hole still becomes localization, because hole chemical potential can be connected with the silver telluride potential web. We measure several reproducible behavior for thermal electrical conductivity, Seebeck coefficient, and power factor shows that very well reproduced for several times. And when you consider for the whole carrier concentration and mobility, and the lead telluride and the bismuth of the lead telluride shows that this behavior, but the small addition of silver telluride and significant decrease of charge localization, because and one order of magnitude whole carrier concentration decreases, and in many cases the decrease of whole charge carrier concentration can increase the whole mobility in many cases, because decrease of electron scattering. But in this case, whole mobility becomes very small, one order of magnitude also decrease. It means that strong charge localization by using the silver telluride. And also because next topic is that topological Anderson transition, but time is limited. Then I will briefly introduce this concept. Basically, and the topological material is that has a linear banded dispersion like this, and the linear banded dispersion gives rise to high mobility of charge carrier because it is a relativistic Dirac equation. But Because basically in this case, complete symmetric symmetry electron in whole band, it means that almost a zero Seebeck coefficient. Therefore, but in the finite energy band gap, it is needed, but we consider in this case, we consider for the partial energy band gap opening in this side. And we try successfully, then the partial energy band gap opening can be possible in terms of quantum phase transition near the topological phase transition, and therefore the partial band gap opening increase thermoelectric properties. This is one example is that the leading selenide system. Leading selenide is a direct materials which have the linear band dispersion, but in this case we adopted the thallium doping in this case, and the thallium doping it induces the breaking of the direct linear band dispersion. We identified that selenium doping adoption means that imperfection or the impurities, it breaks the inversion symmetry, and breaking of inversion symmetry, inversion symmetry gives rise to a topological phase transition. And this we measure the topological phase transition because in the case of topological phase transition, the p-band transition, for example, L3 band transition, p-band to conduction band is forbidden because it is S-band. This is a p-band forms that valence band, the S-band forms the conduction band in conventional semiconductor, but in topological state, p-band, S-band band inverted, and the S-band becomes a conduction band, and the p-band becomes a valence band. Therefore, in the case of p-band transition is forbidden in the TCI state, and by breaking the inversion symmetry, then it becomes a normal state, normal semiconducting state. Therefore, the TCI state can be broken. Therefore, we identified that the increase of GT value significantly by breaking the time reversal, by breaking the inversion symmetry. Then the theoretical calculation show that this band, when we consider only for L band and the band convergence, the GT value can be calculated like this. The additional contribution of GT value enhancement can come from the topological phase transition. Therefore, I can conclude that the Anderson localization itself is detrimental for thermoelectric applications, but selective charge Anderson localization can be possible in terms of this kind of potential barrier control. Therefore, by using this concept, we achieve the high GT value above 2 for n-type is composite. Therefore, another concept is that the topological Anderson transition and thermoelectricity is a very good route to find the high GT value materials. Thank you for your attention.